Okay, our speaker today is Ho Wong from Texas A&M University. I think he's a graduate student last year or possibly second to last year student. His research focuses on, at least partly, on various versions of volume conjecture. And I think today he's going to talk about one of the many versions that he's currently working on. So yeah, Kaho, take your thread. Go on.
Yeah, thank you for the introduction and the invitation. The title of my talk is Asymptotics of the Relative Reshetikhin-Turaev invariance. The relative Reshetikhin-Turaev invariance is a sequence of complex valued invariants for a closed oriented three-manifold M with a colored frame length L inside it. And before going into the details, let me first talk about why we care about the asymptotics of the invariance. Okay, so in three-dimensional topology, there are two different approaches to study the lengths and three manifolds. One is by using quantum topology, and another one is by using hyperbolic geometry. On one side, in quantum topology, there are several invariants of lengths and three manifolds, including the famous Jones polynomials and its generalization, defined by using the representation theory of quantum groups. And the construction is algebraic and combinatorial. On the other side, we have hyperbolic geometry. And in hyperbolic geometry, we can talk about geometric invariance of a three manifold by putting a hyperbolic structure on it. In particular, we can use the techniques from differential geometry to study the manifold, and we can talk about geometric invariance, such as hyperbolic volume of the manifold. Okay, so now we have two different approaches to study three-dimensional topology. And it turns out that these two very different approaches are connected by the study of asymptotics of quantum invariance. And in this talk, what I'm going to do is to give an introduction to the so-called volume conjecture and the asymptotic expansion conjecture for the relative Reshetikhin-Turaev invariance proposed recently by my supervisor Chen-Yang and I. Our conjecture essentially suggests that the asymptotics of the relative Reshetikhin-Turaev invariance capture the hyperbolic volume, the Chen-Simon invariant, and the adjoint twisted Reidemeister torsion of the related three manifolds. All right, so now let me give an outline for this talk. And this talk is divided into four parts. In the first part, I'm going to talk about the volume conjecture for the relative Reshetikhin-Turaev invariance. The volume conjecture essentially suggests that this sequence of complex valued invariants grows exponentially, and the exponential growth rate captures the hyperbolic volume and the Chen-Simon invariance of the related three manifold. Especially in this part, I will discuss how our conjecture unifies the previous famous volume conjectures for other related quantum invariants. After that, I will talk about the asymptotic expansion conjecture for the relative Reshetikhin-Turaev invariance. And the asymptotic expansion conjecture suggests that the asymptotics of the invariance capture the adjoint twisted Reidemeister torsion in some sense. Yeah, and in this part, I will state the statement of our asymptotic expansion conjecture. After that, I will move on to talk about the quantum topology and hyperbolic geometry for a special family of lengths called the fundamental shadow lengths, introduced by Constantino and Thurston. Especially, I will talk about the importance of this family of lengths from topological, quantum topological, and geometric points of views. And we are going to use this special family of lengths to provide supporting evidence to our conjectures. Moreover, I will use this family of lengths to illustrate how quantum topology and hyperbolic geometry interact with each other. And at the end of this talk, I will summarize our recent progress on these conjectures. All right, so now let me first talk about the volume conjecture for the relative Reshetikhin-Turaev invariance. And maybe let me give a brief review about the construction of quantum invariance here. Okay, so first, given an odd integer r equal to 2n plus 1 greater or equal to 3, in this talk, we will focus on the following r roots of unity, q equal to e to the power 2 pi I divided by r. The relative Reshetikhin-Turaev invariance can be defined by using the scheme relation. And to do that, let me first recall the definition of the so-called Kaufman bracket. The Kaufman bracket for a framed length L with a plane diagram D, denoted by the bracket of D, is defined by the following two rules. The first rule is the Kaufman bracket scheme relation, which says that locally, whenever we see a crossing in this form, we can resolve it in these two different ways. And we will put two complex numbers in front of these two resolutions. And after resolving all the crossings, at the end, we will get a bunch of diagrams. Each of them consists of several copies of circles, which are unlinked with each other. And the framing relation tells us that whenever we see a circle which is unlinked with other components, we can replace it by this complex number. So at the end, the Kaufman bracket of the diagram D will give us a complex number. All right, and in scheme theory, there are two special types of diagrams, or to be precise, linear combination of diagrams. First, given a non-negative integer m, we have the so-called nth Jones-Wentzel idempotent EM. And in this talk, I'm going to use a black box with a label M to represent this diagram. Another important diagram is the so-called Kirby covering, omega R. And similarly, I'm going to use a white box to represent this diagram. All right, with these notations, now I can talk about the construction of the relative Reshetikhin-Turaev invariance for a closed-oriented three-manifold M with a colored frame length L inside it. First, we let IR be the set of even integers in between 0 and R minus 2. And IR will be the set of colors in this theory. Then, for a closed-oriented three-manifold M, obtained by doing surgery along a red frame length L prime in SC. Suppose we have a n components blue framed length L inside the ambient manifold M. On each component, we choose a color inside the set IR, and we use the bold letter M to denote the vector connecting the colors. Then the nth relative Reshetikhin-Turaev invariance, or in short, the relative RT invariance of the pair ML is defined by the following formula, which essentially says the following. Suppose the ambient manifold is obtained by doing surgery along this red frame length L prime. And imagine that we have a blue framed length L inside the ambient manifold. Then the relative RT invariance of M of the pair ML with colors M1, M2 is up to some factor equal to the Kaufman bracket of the diagram obtained by putting a Kirby-Carving on the red component and putting the corresponding Jones-Wentzel idempotent on the blue components respectively. In particular, the relative RT invariance will give us a complex number. And for each R, we get a complex number. So now we get a sequence of complex number for the pair ML.
Carl, may I ask some basic questions?
Yes.
Where does this invariant leave?
So this is a complex valued invariance.
Oh, okay.
Okay.
And could you remind me what this black box and the white box do?
The black box is the so-called Jones-Wentzel idempotent, and the white box is the so-called Kirby-Carving. And the reason why we put a Kirby-Carving here is to make sure that this is indeed an invariant. That means the quantity defined in this way is invariant under the Kirby move. Yeah, and that's why this one is called the Kirby-Carving.
Okay.
Okay. All right, so this is the definition of the relative Reshetikhin-Turaev invariance. And here, let me mention two special cases. First, when the ambient manifold M is SC, the relative RT invariance of SC with a Carter frame length inside it is up to some factor equal to the nth Carter-Jones polynomials of the frame length L, evaluated at the root T equal to Q square equal to this n plus 1/2 roots of unity. Besides, if we choose all the colors to be 0, the relative RT invariance we cover the original Reshetikhin-Turaev invariance of the ambient manifold M. So in this sense, the relative RT invariance unified the Carter-Jones polynomials at roots of unity and the Reshetikhin-Turaev invariance of the three manifold. Okay, so now we have a sequence of complex value invariance. And in quantum topology, one important question is to ask what is the topological and geometrical meaning of the invariance. And in this talk, we are going to focus on the relative RT invariance of a pair ML. We call that the parameter R is defined to be 2n plus 1. On one side, we are going to choose all the colors M to be capital N. And you may regard this as an analog of the nth Carter-Jones polynomial of L, evaluated at this n plus 1/2 roots of unity. On the other side, we are going to choose all the colors to be equal to 0. And in this case, we'll get the Reshetikhin-Turaev invariance of the three manifold M. And what we are going to study is the corresponding picture in hyperbolic geometry. All right. So last year, joined with my supervisor Chen-Yang, we proposed the following volume conjecture for the relative Reshetikhin-Turaev invariance. First, for a sequence of colors MR equal to M1R up to MNR inside the set IR to the power n, we consider the quantity theta k defined by this formula. And this quantity is essentially the absolute value of the difference between 2 pi and the linear growth rate of this sequence of colors, MKR. And since each MKR is inside the set IR, one can verify that theta k is in between 0 and 2 pi. And we will let theta equal to theta 1 up to theta n. Then we propose that if ML theta is a hyperbolic cone manifold consisting of M and a hyperbolic cone metric on M with singular locus L and cone angles theta, then the relative RT invariance of the pair ML with this sequence of colors MR grows exponentially in R. And the exponential growth rate captures the hyperbolic volume and the Chen-Simon invariance of the cone manifold in the following sense.
So I have a question.
Yes.
So how, when you take the logarithm of RT, how do you choose the branch?
Yeah, good question. Yeah, I think we can just use the standard branch. I mean, so that means when we take argument, we require to be within negative pi to pi. Yeah.
Okay.
Okay.
Sorry, I mean,
Yes.
what if the argument lies on the pi, like the branch card? Like, did you just choose a random random value?
Yeah, let me see.
Let's say, like, if RT, the value of RT is -1, how do you take the logarithm?
I see. Yeah.
Or maybe it's never equal to -1. Then that's fine. Oh.
Yeah. Yeah, I see. Okay, so I think maybe to make this statement more precise, so I think maybe a better way to say is that, so assume that we know the value of the Chen-Simon invariance, then probably we need to take a suitable branch that avoid this, that we need to choose a suitable branch such that the Chen-Simon invariance is inside this branch. Yeah, then when our scope is sufficiently large, then everything will be within the branch. Yeah, so we won't have the problem. Yeah.
Okay, good. Thank you.
Right, so this is our volume conjecture for the relative Reshetikhin-Turaev invariance. And in fact, our conjecture is closely related to other volume conjecture in quantum topology. First, we call that we define R to be 2n plus 1, and we define the cone angle theta k by this formula. First, when the ambient manifold M is S3, and if we choose all the colors to be capital N, since the relative RT invariance is up to some factor equal to the nth Carter-Jones polynomial of the length L, evaluated at this n plus 1/2 roots of unity. And by direct computation, when all mkr is equal to capital N, theta k's are all equal to 0. So in this case, we will get a cusp manifold. And our conjecture will suggest that for a hyperbolic length L, the nth Carter-Jones polynomial of L evaluated at this n plus 1/2 roots of unity grows exponentially. And the exponential growth rate captures the hyperbolic volume and the Chen-Simon invariance of the length complement. And this statement can be regarded as an analog of the famous Kashaev-Murakami-Murakami volume conjecture for the Carter-Jones polynomials. Or more precisely, the complexified volume conjecture proposed by Murakami, Okamoto, Takata, and Yokota. Besides, if we choose all the colors to be equal to 0, in this case, the relative RT invariance recovers the original Reshetikhin-Turaev invariance of the ambient manifold M. And when all mkr is equal to 0, this term disappears. So theta k's are all equal to 2 pi. Especially since the cone angle are all equal to 2 pi, L is no longer a singularity. So in this case, we will get a closed-oriented hyperbolic three-manifold. And our conjecture suggests that the Reshetikhin-Turaev invariance of M also grows exponentially in R, and the exponential growth rate captures the hyperbolic volume and the Chen-Simon invariance in this sense. And this statement is nothing but the Chen-Yang volume conjecture for the Reshetikhin-Turaev invariance of closed-oriented three-manifold. All right, so now let me give a brief summary about what I have discussed so far. In this talk, we focused on the relative RT invariance of a pair ML. On one side, we are going to choose all the colors to be capital N. And you may regard this as an analog of the nth Calder-Jones polynomials of L evaluated at this n+1/2 roots of unity. On the other side, we will choose all the colors to be equal to 0. And in this case, we'll get the Reshetikhin-Turaev invariance of the ambient manifold M. Then, in terms of hyperbolic geometry, going from the left-hand side to the right-hand side, we change the cusp manifold with complete hyperbolic structure to the cone manifold with incomplete hyperbolic structure all the way to the closed manifold obtained by doing Dehn-filling on the original cusp manifold. And the cone angle changed from 0 to 2 pi according to this formula. So in this sense, our conjecture can be understood as an interpolation between the Kashaev-Murakami-Murakami volume conjecture for the Calder-Jones polynomials and the Chen-Yang volume conjecture for the Reshetikhin-Turaev invariance. Especially, our conjecture provides a new approach to study the Chen-Yang volume conjecture by pushing the cone angle from 0 to pi. And I will come back to this point later in this talk. All right, so far we have focused on the exponential growth rate of this sequence of invariants. And it turns out that this is not the end of the story. By studying the Ho Asymptotics expansion of the relative Reshetikhin-Turaev invariance, we can actually obtain another important invariant in three-dimensional topology, which is the adjoint twisted Reidemeister torsion. So now let me talk about the asymptotic expansion conjecture for the relative Reshetikhin-Turaev invariance. All right, so now we let M be a closed-oriented three-manifold, and we let L be a framed hyperbolic link in M with n components. And then we let MR equal to M1R up to MNR be a sequence of coloring such that for each k equal to 1 up to n, when R is sufficiently large, either MKR is strictly greater than R over 2, or MKR is strictly less than R over 2. Then we define the cone angle theta KR similar to what we did in volume conjecture. And by the assumption on MKR, when we remove the absolute sign, we'll get an extra factor mu k equal to plus or minus 1, such that this equality holds. And then in the statement of asymptotic expansion conjecture, we will assume that all the cone angles theta k are greater or equal to 0, but strictly less than 2 pi for R sufficiently large. And then we let nu equal to nu1 up to nu n be the system of meridian around the frame length L. And we let gamma 1 up to gamma n be the parallel copies of L1 up to Ln defined by the framing. And in particular, we can talk about the logarithmic holonomy of gamma I, and we will use H gamma I to denote the logarithmic holonomy. Okay, so with all this notation, the asymptotic expansion conjecture can be stated as follows. So recently, joint work with Chen-Yang, we proposed that suppose for R sufficiently large, a hyperbolic cone metric on M with singular locus L and cone angles theta R exists. And we denote M with such a hyperbolic cone metric by MR. Then we propose that as R varies over all positive odd integers, and at Q equal to e to the power 2 pi I over R, this particular word of unity, the relative RT invariance has the following asymptotic expansion formula. And this formula consists of several parts, and let me talk about them one by one. First, in the exponential part, we get the hyperbolic volume and the Chen-Simon invariance, similar to what we have seen in the volume conjecture. And then in front of the exponential part, here on the denominator, we'll get the square root of the adjoint twisted Reidemeister torsion of the length complement in M with respect to the system of meridian nu associated with the holonomy representation coming from the hyperbolic cone structure MR. And on the numerator, we'll get exponential of 1/2 of the signed sum of the holonomy of the curve gamma k. And at the front, we have a quantity C, which is just a quantity of log 1 independent of the geometric structure on M. And the error term in this asymptotic expansion is of order big O 1 over R. All right. And here, let me give two remarks about our asymptotic expansion conjecture. First, I would like to point out that there are other asymptotic expansion conjectures. In particular, there are asymptotic expansion conjectures for the Carter-Jones polynomials and for the Reshetikhin-Turaev invariants. For example, by using complex Chen-Simon theory, Gukov proposed an asymptotic expansion conjecture for Carter-Jones polynomials of not in SC. And besides, Osuki proposed an asymptotic expansion conjecture for the Reshetikhin-Turaev invariance of closed-oriented three-manifold, and he proved his conjecture for all three-manifold obtained by doing integral surgery on the figured X0 complement. In addition, by using complex Chen-Simon theory, Gan, Wormel, Yamasaki proposed an all-order volume conjecture for the Reshetikhin-Turaev invariance. And in all this conjecture, we can see the hyperbolic volume, the Chen-Simon invariance, and the adjoint twisted Reidemeister torsion of the related three manifolds. Okay, so that's the first remark. Another remark is that for a given sequence of cone angles theta R, the asymptotic expansion conjecture implies the volume conjecture. And it is essentially because of this part in the asymptotic expansion formula. Okay, so now we have two conjectures. And in the third part of this talk, I'm going to talk about the quantum topology and hyperbolic geometry of the so-called fundamental shadow lengths. And later we'll use this family of lengths to provide supporting evidence to our conjectures. Okay, the family of fundamental shadow lengths was introduced by Costantino and Sexton. And first of all, let me tell you the construction of this family of lengths. The building block of this family of lengths is the so-called truncated tetrahedron, delta. So it is basically an ordinary tetrahedron with all vertices removed. And to construct a fundamental shadow length, first we take C copies of building blocks, delta 1 up to delta C. And then we glue the building blocks together along the triangles of truncation. That means these little triangles on the building block. So we glue them together via homeomorphism to obtain a possibly long-orientable handle body of genus C+1 with a length in its boundary consisting of the edges of the building blocks. And the last step in the construction is to take the orientable double of the handle body to change the ambient manifold into connected sum of S2 cos S1, which is a closed oriented three-manifold. And a length constructed in this way is called a fundamental shadow length. And here, let me give you an example to see how we can obtain a fundamental shadow length. So here, I pick exactly one building block. And what I'm going to do is to glue these two faces together and glue these two faces together to get a handle body of genus 1 + 1 = 2. Especially, you will see that the endpoints of these green edges are glued together to form this component on the right-hand side. And similarly, the endpoints of this orange edge are glued together to form this component. And the remaining 4 blue edges are glued together to form the remaining components. And the last step is to take the double of this handle body to change the ambient manifold into connected sum of S2 cos S1. And a length constructed in this way is called a fundamental shadow length. And here you may think that the construction of this family of lengths is too artificial. So why do we care about it? Okay, so first, in this talk, I'm going to consider the whole family of fundamental shadow lengths. And for simplicity, I will call this pair a fundamental shadow length pair. So this is a connected sum of S2 cos S1, and this is a fundamental shadow length. And it turns out that by result of Costantino and Thurston, any compact oriented three-manifold with toroidal or empty boundary can be obtained from a suitable fundamental shadow length complement by doing an integral Dehn-filling to some of the boundary components. Therefore, this family of lengths is universal in this topological sense. Besides, quantum topologically, the nth relative RT invariance of a fundamental shadow length pair has a very nice formula, and it is essentially given by the product over the building blocks of something called quantum Secret symbols. The quantum Secret symbols is a invariance associated with 6 colors, M1 up to M6. And by result of Costantino, it turns out that for a suitable choice of sequence of colors, M1R up to M6R, this invariance also grows exponentially. And the exponential growth rate captures the hyperbolic volume of the so-called hyperideal tetrahedron with dihedral angles θ1 up to θ6 determined by M1R up to M6R respectively. And we will come back to this point later in this talk. Moreover, Benetti, Detri, Calfagiani, and Yang proved that the volume conjecture for the fundamental shadow length pair with all colors chosen to be capital N is true. And because of all these nice properties satisfied by the family of fundamental shadow lengths, we would like to study our conjectures for this family of lengths. And now, let me talk about our recent progress on the volume conjecture and the asymptotic expansion conjecture. First, for the volume conjecture, last year, joined with Chen-Yang, we proved that if ML is a pair such that, first, the complement is homomorphic to some fundamental shadow length complement, and if the ambient manifold M is obtained by doing an integral surgery on some boundary components of the fundamental shadow length complement, then our volume conjecture is true for this type of pair ML with sufficiently small cone angles. And here, I would like to give two important remarks about our results. First, in theorem 1, the ambient manifold M is obtained by doing integral surgery on the fundamental shadow length complement. So together with the result of Costantino and Thurston, the manifold M in theorem 1 actually closed-oriented manifold. And in theorem 1, we proved the volume conjecture for sufficiently small cone angles. And if one can push the cone angle from sufficiently small all the way to 2 pi, then one can prove the Chen-Yang volume conjecture for the Reshetikhin-Turaev invariance of closed-oriented manifolds. Okay. So we call that our conjecture provide a new approach to study the Chen-Yang volume conjecture by pushing the cone angle from 0 to 2 pi. And in order to show that this approach is at least possible, last year, joined with Tian-Yang, we proved that our volume conjecture is true for all pair ML with complement homeomorphic to the figure 8 knot complement for all cone angle from 0 to 2 pi, except finally many cases corresponding to the exceptional surgery of the figure 8 knot. Okay, so this is the result for the volume conjecture. And for the asymptotic expansion conjecture, recently, with Chen-Yang, we studied the pair mentioned in theorem 1. That means we consider those pair ML such that first, the complement is homeomorphic to some fundamental shadow length complement, and the ambient manifold is obtained by doing integral surgery on a fundamental shadow length complement. If ML satisfies these two properties, then we prove that our asymptotic expansion conjecture is true for sufficiently small cone angles. And later, joined with Tusha Pandey, who is another graduate student in Texas A&M University, we generalized theorem 3 by allowing the ambient manifold M to be obtained by doing rational P over Q surgery on the fundamental shadow length complement, with under a technical assumption, the denominator of the surgery coefficient is odd. Yeah. So theorem 3 and theorem 4 provide infinitely many supporting evidence to our asymptotic expansion conjecture.
I have a question.
Yes.
Can you go back 2 slides, please?
Okay.
Yeah. So in this table, yeah, just this slide.
Table. Okay.
Yeah. So in this slide, you said this cone angle 0 corresponds to the Kashaev volume conjecture.
Yeah. The cusp.
And for cusp manifold. So does this include the original volume conjecture?
Not exactly. The reason is that in the statement of the Kashaev-Murakami-Murakami volume conjecture, they consider the root e to the power 2 pi I over n.
Yes.
And here we consider n plus 1/2.
Okay, and you so in the next theorem, I think theorem in the next slide, you mentioned your theorem is true for all cone angles sufficiently small. So does that include the case of cone angle being 0?
Yes. Yeah, that means prove the conjecture for cone angle from 0 to some epsilon, where epsilon is some number greater than 0.
Okay. Sir, does this imply the volume conjecture for knots when you change the root of unity to the one you wrote in the previous table?
Yeah, so that means if we consider the relative RT invariance of this pair, and then if we choose all the colors to be capital N, so this in this case, we can prove that the volume conjecture and the asymptotic expansion conjecture is true. Yeah.
Okay, and in particular, I can choose M to be the 3 sphere, and you prove the volume conjecture for this root of unity.
No, because we need these two assumptions.
Okay.
Of course,
So
if you find if the ambient manifold is SC, and if you somehow can find a length L such that the pair SC L satisfies this property, then yes.
Okay, I see. I got it. Thank you.
All right. And in the remaining part of this talk, I'm going to talk about a key part in the proof of theorem 3 and theorem 4. So we call that the asymptotic expansion conjecture suggests that the relative RT invariance capture the adjoint twisted Reidemeister torsion. In particular, in order to prove theorem 3 and theorem 4, at least we need to know how to write down the adjoint twisted Reidemeister torsion of a fundamental shadow length complement. And how to do that? So we call that the relative RT invariance of a fundamental shadow length pair can be expressed as the product of the so-called quantum sigma symbols. So in order to get some feeling about how the adjoint twisted Reidemeister torsion may look like, it is natural to look at the asymptotic expansion of each quantum sigma symbols. And it turns out that it is closely related to something called ground matrix, which is defined as follows. First, given 6 complex number, U1 up to U6, the ground matrix function evaluated at U1 up to U6 is defined to be the following 454 matrix with complex entries. And the entries consist of 1 and negative cos of U1 up to U6. And it turns out that by result of Chen and Murakami, for suitable choices of sequence of colors M1R up to M6R, the quantum sigma symbols has the following asymptotic expansion formula. And geometrically, the quantum sigma symbols M1R, M1R, M4R, M2R, M5R, and M3R, M6R. So these colors correspond to the pair of opposite edges 1, 4, 2, 5, and 3, 6. And the limit of the linear growth rate of this sequence of R determined the dihedral angles of this hyperideal tetrahedron by this formula, which is similar to what we have seen in the volume conjecture. And from the asymptotics of the quantum sigma symbols, we get the hyperbolic volume of the hyperideal tetrahedron. And in front of the exponential part, here we get the square root of the determinant of the ground matrix function evaluated at I times the dihedral angles. So inspired from this asymptotic expansion formula, it is not too surprising that the adjoint twisted Reidemeister torsion of a fundamental shadow length complement is related to the square root of the determinant of the ground matrix function. And to make this statement precise, I need to tell you how to assign the ground matrix function to each building block of the fundamental shadow length complement. Okay, so how to do that? First, we let M be a fundamental shadow length complement obtained from C building blocks, delta 1 up to delta C. And we assume that the fundamental shadow length has n components. And then we let chi naught of M be the distinguished component of the SL2C character variety of this manifold with torus boundaries. And we let nu equal to nu1 up to nu-n be the system of meridians of the tubular neighborhood of the fundamental shadow length. And in particular, at least around the complete hyperbolic structure, we can talk about the logarithmic holonomies of the curve nu1 up to nu-n. And this gives us C complex number. And then for each k equal to 1 up to C, that means for each building block, we will let LK1 up to LK6 be the components of the fundamental shadow length intersecting delta K. And we will let GK be the ground matrix function evaluated at half of the logarithmic holonomies. So this sounds a little bit complicated. So let's look at the example we discussed before. So here we have one building block, and then we glue these two faces together and glue these two faces together to get the handle body on the right side. In particular, this green edge will become this length components, and this orange edge will become these components, and the remaining four blue edges are glued together to form the remaining components. And then on the right-hand side, we can talk about the logarithmic holonomy. Let's say here we have h of nu1, here we have h of nu2, and we have h of nu3 here. And you can see that the logarithmic holonomies on the right-hand side naturally induce an assignment of 6 complex number to the edges of the truncated tetrahedron. So once we have 6 complex number associated with the building block, we can talk about the associated ground matrix defined in this way. All right, and joint work with Chen-Yang, we proved that for a generic irreducible character rho in the distinguished component of the SL2C character variety of the fundamental shadowing complement, the adjoint twisted Reidemeister torsion of M with respect to the system of meridian nu associated with this character rho is up to some factor equal to the product of the square root of the determinant of the ground matrix function. And here, let me give one more important remark that as a consequence of theorem 5, I mean this formula, together with the so-called change of curve formula and the surgery formula for the adjoint twisted Reidemeister torsion, we obtain an explicit formula for the adjoint twisted Reidemeister torsion of any closed hyperbolic three-manifold obtained by doing hyperbolic Dehn-filling on a fundamental shadowing complement. And the formula looks like this one. And the importance of this formula is that by the universality of the fundamental shadow length and by the Thurston hyperbolic Dehn surgery theorem, our formula actually covers most hyperbolic three manifolds. And to the best of our knowledge, this is the first formula for the adjoint twisted Reidemeister torsion for most hyperbolic three manifolds. All right, so I think that's basically what I want to discuss in this talk. And thank you very much for your attention.
Thank you. Are there any questions for Kaho? I have a few questions, but I just want to ask if any other people have questions.
I have a basic question.
Yes.
Why does volume plus I Chern-Simons show up in many places?
Yeah, I'm not sure if I can give a good explanation. There is some physical interpretation for the quantum invariants, such as the Carter-Jones polynomials. And I think there is some physical argument suggesting, telling us why we should get the volume plus I Chern-Simons. Yeah, but I'm not so sure about that story. Yeah, so I think I may, yeah, I think I cannot give a good answer from a physics point of view. Yeah.
It's quite surprising to me. I'm not familiar with the story of torsions, but for example, I'm interested in group homology of PGL2C. And if you have a hyperbolic three-manifold, then you have a map from the fundamental group of the hyperbolic three-manifold to PGL2C. And this way you get element in the third group homology of PGL2C. And again, this invariant of volume plus I times Chern-Simons give you group homology element of PGL2C.
Yeah.
Which is, yeah, I thought that maybe there is some conceptual reason that this invariant is very important.
Yeah. Yeah, I don't know. I think what you mentioned is related to something called Bloch group and something called Borel regulator.
Yes,
yeah.
yes.
Yeah, there is a theory about that, but I'm not familiar with that part of the story. Yeah, I'm sorry about it.
Yeah, I thought, a volume is an important invariant and Chern-Simons is also important, but why should we build a complex number out of it? So anyway, thanks.
Yeah.
So actually, I also would like to ask some questions. First of all, for the original volume conjecture,
yes.
Did the result manage to give any new examples? For example, figure not known already, but do you give new examples, new cases of volume conjectures that are not known?
Okay.
In other words, could you check your criteria somehow for some new examples of hyperbolic threefolds?
So, okay, so in our, let's say in theorem 1, we study our version of volume conjecture for this type of pair. And yeah, so in particular, here, by sufficiently small cone angle, we also include the angle 0. Yeah, so in this sense, our theorem also provides you example to the analog of the Kashaev-Murakami-Murakami volume conjecture. Yeah, but our conjecture is kind of independent from the Kashaev-Murakami-Murakami volume conjecture in the sense that we are considering different roots of unity. So for example, if we note that a lot satisfies the Kashaev-Murakami-Murakami volume conjecture, it doesn't imply that it satisfies our volume conjecture because we are considering two different roots of unity. Yeah, but I would like to point out that in fact, for the original Kashaev-Murakami-Murakami volume conjecture, there is not an analog for length. To be precise, if we consider the Carter-Jones polynomial of length, then there is a counterexample showing that the Carter-Jones polynomial does not grow exponentially. So that's, but if we change the roots of unity, actually we can, at least we can kind of propose a volume conjecture that also includes length in SC. Yeah. So that's one of the advantage of changing the roots of unity.
Okay, so I would also, thanks. I would also have one more question. So suppose if you take a hyperbolic manifold, you take a magnified covering, say you have a fundamental gamma there. Suppose you take a lattice of finite index, normal subgroup there, a subgroup of finite index. So then you have another hyperbolic manifold, and the volume is changed by an integer, right? It's possessed by the index. So my question is that if you take a tower of such coverings, how is it reflected? Is it immediately clear that in your setting, whether it's the torsion or your formula, it's clear that it will be true if one is true?
Yeah, I think the answer is no, because let me see. To the best of my knowledge, I think so. That means, so let's say we have an M manifold M, and then we have another manifold, let's say M tilde, which is a coupling of M. Then if we consider the, let's say the original Reshetikhin-Turaev invariance, I think there is not a clear relation about how these two invariants is related.
The covering is obtained, say, from a normal subgroup of from a normal subgroup of finite index.
Yes, yeah, but still,
we don't know how to do.
Yeah, at least I don't know how to relate these two invariants. Yeah.
Okay. Thank you. But if you consider the decomposition under all your assumptions, wouldn't you have some information about that? I mean, the same basic pieces are obtained from pulling back.
Yeah, because the problem is that, let me go back to the definition of the relative RT invariance. Yeah, because in the definition of the invariance, we define it by using a surgery representation. And let me see. So suppose M is obtained by doing surgery on L prime. And now if we have a, let's say, a finite cover of this manifold, do we know how to present the manifold by using a frame length?
There's a question, yeah.
Yeah, I don't, yeah, at least I don't know, but yeah, I don't know how to, so at least from this definition, it is not clear how the relative RT invariant is related to each other. And then, yeah, and then even if they are somehow related to each other in some sense, we still need to check those, we still need to check another technical assumption when we, because when we prove the volume conjecture, we need to apply several technical tools such as the Poisson summation formula and saddle point approximation, that kind of stuff. And when we do that, we also need another technical assumption for analysis that I do not stay here. Yeah.
Okay. All right. Thank you.
Yeah.
Yeah. So Kaho, since you mentioned that you used this saddle point approximation, I also remember in some of the early proofs for the original volume conjecture for some of the examples.
Yes.
I think most of them, if not all, use this kind of a saddle points method.
Yes.
So are your proofs kind of does your proof have something new or different from their proof so that you can prove this? Your case apparently is more general than theirs, than the original ones.
So maybe let me say a few words about how to apply the saddle point approximation. So very, very roughly speaking, if we skip all the technical details, essentially the idea is that, let's say we start with a quantum invariance. We can use something called Poisson summation formula. To write the invariance into the following form. So it is an integral over some surface D or some domain D, and then the integrand is of the form Fz exponential RGZ dz. And the so-called saddle point approximation suggests that the large R behavior of this type of integral is determined by certain critical points of this function gz. So I think one of our contributions is to relate the critical value of this mysterious function with the geometry of the link complement. In particular, we kind of one contribution is that for the fundamental shadow length complement, we can talk about the so-called Neumann-Zagier potential function. Which is a very important function in hyperbolic geometry. And by using not this so-called Neumann-Zagier potential function, we can compute the volume of the manifold obtained by doing surgery on the original cusp manifold. Yeah. So I think one of our contributions is to relate the critical point equation of this mysterious function with the PQ surgery equation. I mean the PQ P1 hyperbolic Dehn surgery equation of the manifold. And I think this is new. Yeah, this result is new. Yeah. And in general, I think people expect that this type of phenomenon happens, but no one can prove it rigorously. Yeah. And that's how we relate this purely algebraic object with the geometry of the manifold.
Okay. Yeah. Thank you. Are there any other questions?
Can I have a short speculative question?
Yes.
About classical Reshetikhin-Turaev invariant, well, the color-Jones polynomial that is used in the classical volume conjecture is related to the representation of SL2.
Yes.
Can you sort of interpret this relative Reshetikhin-Turaev invariance as some kind of representation theory of something, maybe of some deformation of SL2? Do you know of any work in this direction?
No. Yeah. I'm sorry, but I don't know.
So are you aware of any algebraic interpretation of this, of any sort of this relative invariance? I know it's purely speculative, but
yeah, I'm not sure if I understand your question correctly. So, are you going to change the Lie group, or are you going to find?
I was rather thinking about some deformation of SL2, maybe in some sense of I don't know.
By definition, quantum group is already kind of deformation of the original Lie group.
Yeah. So, but here you have a much richer, more parameters. So can you? Because there you have just n as an integer in the classical situation, but here you have these m i's. They can be. Okay, maybe I would reformulate and email the question.
Okay, yeah.
Okay, thank you.
Yeah, okay.
Are there any questions? So let's thank Kao again. I'm gonna stop the recording.